So the first question asks about just whether or not it's discrete or continuous. So when it says to state whether the variable or the number of cups of coffee sold in the cafeteria during lunch, that would be what? Discrete. Okay, very good. It's something that we would count. Versus the temperature in degrees Fahrenheit in July is continuous. Things that we measure, things that take on an infinite number of values over a certain range, that's what we call continuous data. Okay? All right, number 3. The random variable x represents the number of credit cards that adults have along with the corresponding probabilities. Find the mean. Okay, the formula for the mean is mu equals the summation of x times p of x. This is for probability distribution in general. Okay, so we just have one. We don't know anything about it being binomial or normal or anything like that. So what we could do is actually go through and multiply each x by the corresponding p of x and add all of those up. Okay? Or, if you wanted to, we could use our calculator. And we're going to put the x values in a list and the p of x values in a list. Okay, so we get I'm going to go to stat. Okay, and edit. So my x values were 0 through 4. And my probabilities are, okay, 0.49. Okay. And 0.07. All right. Okay, and we should probably check to make sure that those probabilities add up to 1, to make sure that it's a valid probability distribution. But once we've got them in the calculator, we're going to go to Stat, go over to Calc, and we're doing this just like we would a weighted mean. So it's one variable stats. We're going to look at L1, comma, L2. And so we get x bar is equal to 1.18. Okay, that's our mean. All right, the mean of this probability distribution is 1.18. We had some, I think, some interesting situations before where it didn't exactly add up to 1. But in a simple case like this, it should add up to exactly 1, and that'll take care of it. I think the next question probably asks us to find the standard deviation for the same data. And so the standard deviation is here. We would say sigma is equal to looks like it'd be 1.3. Okay, questions about that? Can you see oh, you want to see the choices? You don't think I'm right, okay? All right, 1.18, and I had 1.3. Okay, questions?
So the standard deviation is that same list on the calculator, just on the bottom?
It was sigma. Mm-hmm. Sigma x is our standard deviation. Okay? Alrighty. Okay, with this next one, I think they ask us to find the expected value. But remember, with the expected value, we first have to come up with the probability distribution. So it says 1,000 tickets are sold at $1 each. One ticket will be randomly selected, and the winner will receive a color television valued at $350. what is the expected value if a person buys one ticket? Okay, so again, we got to come up with the probability distribution, and X is going to be the value to the person playing the game, and P of X is going to be the probability associated with that value. What are the possible values that a person can have if they play this game? What can happen if the person plays the game? They either what? Win or lose, okay? So if they win, they get what? Okay, TV valued at $3.50, except they paid $1. So they get a value of $349. That's what they gain. Or if they lose, then what? They just lose $1. Okay? Since 1,000 tickets are sold, and we can assume that one of those tickets, it says one ticket will be randomly selected, and that's the winner. What's the probability of them getting the $349? 1 out of 1,000. And then the probability that they lose $1 is what? 999 out of 1,000. Okay, so that's the probability distribution. And then from there, we can calculate the expected value, which is just another name for the what? For the mean. Expected value is just the summation of X times P of X. Or, in this case, we get 349 times 1 over 1,000. So I'm just put 349 over 1,000. Okay. Minus 999 over 1,000. Okay, and that looks like that's going to be what? Negative 659 over 1,000. Which reduces to 0.65. Okay. 0.659. Okay. All right, so that would be the expected value. Questions about this?
Is there a reason we use the X on win and the PX?
Now, when we construct the probability distribution, we have to list all of the possible values. Those are X's, and the probabilities associated with each one. So for win, the X value is 349, and for lose, the value is -1. And then the probability of you winning is 1 over 1,000. Right. It's X times P of X. So, and then we took this X and multiplied it by P of X. It's P of X. Okay? All right, questions. Now, as we're doing this, you might just want to make a checklist of concepts, that we've talked about, because these are the very things that we've talked about, and sometimes they almost appear in the order in which we talked about them. Okay? So, next thing, here, we've got a word problem. It says, in a recent survey, 80% of the community favored building a police substation in their neighborhood. If 15 citizens are chosen, find the probability that exactly 10 of them favor the building of the police substation. All right, so when you look at this problem, probably from here on out, we need to ask ourselves, what type of probability distribution does this have? Okay, and we could kind of break that down into, is it binomial? Is it normal? Should we use the central limit theorem? Should we use a normal approximation to the binomial? Okay, when we look at this, what do we see? Or which of those does it satisfy? Okay, is it binomial? Okay. All right. How do you decide if something is binomial? We have to have what? 4 requirements. First, we have to have 2 outcomes, right? Okay, probability of success is the same for each trial. We have a fixed number of trials, and the trials are independent. Okay, do we have that in this case? You still say no? Okay, well, what are the outcomes if we ask a person, how do you feel about us building this police substation? They could say what? They could say, yes, I'm in favor, or no, I'm not. So that's 2 outcomes. Okay, do we have a fixed number of trials? Yeah, we're looking at this as it relates to when we talk to 15 citizens. So we have a fixed number of trials. What about the probability of success? Is it the same from trial to trial? Yes, okay. And if these people are randomly selected, then they are independent. What one says has no bearing on what the next person is going to say. All right? And it doesn't affect that probability. So this is binomial. And so we're looking for the probability that exactly 10 of them favor the building of the police substation. Okay? We use the calculator to help us with this. I would use Binom PDF. Okay, where it asks me for N, P, and X. Okay, where N is that fixed number of trials, P is the probability of success, and X is the exact number of successes that we're interested in. So for us, N is 15, P is 0.8, and X is 10. Okay, so on our calculator, we can do, we're going to do second vars binom PDF, which is alpha A. N is 15, P is 0.8, X is 10. All right, and so we get 0.1032. Okay, 0.1032. Yes, 0.103. Okay. Questions about that? All right, so just in your kind of checklist, ask yourself, could this problem be binomial? All right, it's got to be some of the things that we talked about. All right. Okay, number 7. 50% of the people that get mail order catalogs order something. Find the probability that only 4 of 10 people getting these catalogs will order something. Okay, could this be binomial? Okay, yes. All right, how do we know? You think there's more than 2 outcomes? There are only 2 outcomes. They're either what? Order or don't order. Buy or don't buy. Okay. Do we have a fixed number of trials? Yes, we're looking at 10 people. Right. Probability of success. Is it the same from trial to trial? Yes. Okay. And the trials are independent if these people are randomly selected. So this meets the requirements of the binomial. Again, we are interested in exactly 4 getting something from the catalog. So we're going to use, again, Binom PDF. N is what? 10. P is 0.5. And X is 4. Okay, very good. You have to put it in that order. NPX. Okay. And so we get 0.2051. Okay, so choice A here. Okay, questions about that? Alrighty. Question 8. According to government data, the probability that an adult was never married is 15%. In a random survey of 10 adults, what is the mean of the number never married? Okay. Even if we're going to talk about the mean, we still need to know something about the distribution. Either we need to have the probability distribution listed here, or maybe we have some shortcuts if we happen to know what the distribution is. So what kind of distribution do we have in this problem? Is it binomial? What is that? It's not binomial? Okay. Alright, how do you know it's not binomial? Which of the 4 requirements of binomial does it not meet? Do we have 2 outcomes? Yes. You either married or you didn't. Do we have a fixed number of trials? Yes. Probability of success, is it the same for each trial? Yes. Are the trials independent? Yes. Is binomial. Okay, that's the only way to know if it's binomial, is you've got to go through those 4 requirements, which means you have to know the 4 requirements. So it is binomial, and the question asks us about the mean. We said for the binomial, the mean is n times p. Okay, that's our formula for finding the mean for a binomial. And so in this case, n is what? 10. P is 0.15. So we multiply those 2 together, we get 1.5. Okay, that's the mean number of people, long run average number of people out of 10 who never marry. That's all you have to do. But you got to know first that it's binomial, and you need to know the formula for the mean of a binomial distribution. Okay. All right, number 9. According to police sources, a car with certain protection system will be recovered 90% of the time. If 100 stolen cars having this protection system are randomly selected, what is the standard deviation of the number of cars recovered? Okay, they've asked us for the standard deviation. Okay, except first we need to know what? What kind of distribution does it have? And we might start by asking, is it binomial? Is it binomial? Yes. Okay, because the car will either be what? Not stolen or not, but well, recovered or not. Those are the choices, okay? Because it says we have 100 stolen cars. We want to know if they're recovered or not. Okay, do we have a fixed number of trials? Yes. Probability of success, is it the same for each trial? Yes. Trials independent? Yes. Okay, what is the formula for the mean, not the mean, but the standard deviation of a binomial? Well, in general, that's true, but for a binomial, what is it? MPQ, square root of n times p times q. Okay, that's for a binomial only. Okay, if you looked at that Poisson distribution, they had a different formula for the mean and standard deviation of it. Okay, you know, depending on what the distribution is, we can find come up with a shortcut for the mean and standard deviation. So this applies to a binomial. Okay, n in this case is 100, p is 0.9, and q is what? 0.1. It's 1 minus p. Okay, so we get 9. No, we get 3 when we take the square root. Which one? That's just the relationship between the standard deviation and the variance. Yeah. No matter what type of distribution. Only if you had the variance of the binomial distribution, but you're not going to have that. We'll have like a problem just like this. Okay? What that was talking about was if I know that the variance is, let's say, 16, then the standard deviation is 4. That's all I need to know to figure that out. Okay? Okay. Alrighty. So I think that's going to be all of our examples for binomial for now. Alright, so then we've got a few examples that kind of get us warmed up to the normal distribution table. Okay, so we've got the probability that 0 is less than z is less than 1.5. So we could either use our table or we can use our calculator. I'll use the calculator. We used second distribution. We're doing normal CDF. We put in the lower bound, which I believe is 0, and the upper bound, which is 1.5. Is that right? And so we get 0.4332. Oops, that's my answer. This one. 0.4332. Okay, questions about that? Because the syntax for that normal CDF is lower bound, upper bound. So in this case, the lower bound, we were looking at this thing from 0 to 1.5. So here's my normal distribution. 0's at the center. 1.5 is here. And that's it. Yes. Okay. You had a question? Okay. Alright, same thing with this next one. We've got probability of 0. 0.72 is less than z is less than 2.15. So on my calculator, I could look at number 2. Okay, what was the first number? 0.72 and 2.15. And so we get 0.21998. So we're going to have to call that 0.22. Okay, so that's just kind of testing, making sure that you either know how to use the table or the calculator. And we always need to know what the distribution is, and in this one they tell us it's what? Normally distributed. Okay, and in general, when we know something is normally distributed, then in an application like this, we start with a given x value. We're going to convert that to a z-score, and then we're going to use our calculator or the table to come up with the probability. Okay, so they're asking us to find the probability of a pregnancy lasting less than 250 days. So the probability that x is less than 250. Okay, I've got to convert that to a z-score. I can do that because they've already told me that this thing is normally distributed. Okay, so my z value is 250 minus the mean of 268 divided by 15. Okay, so we get 250 minus 268 divided by 15. Okay, very good. So we're looking at the probability that z is less than negative 1.2. Okay. Now, well, then we still got to find the probability. And so we could use our calculator to help us find that. In this case, negative 1.2 is right here. And that's my upper bound. I want to be less than that. So my lower bound is what? Okay, minus infinity. And so we'll just put in a negative, big negative number. So we're going to do second distribution. Normal CDF is number 2. I've got minus 10 gazillion, okay, to minus 1.2. That's my upper bound. And so we get 0.1151. Okay, questions about that?
Will it know your answer if you put in a negative smaller value that's too small?
No, as long as, really, I don't think it's going to make a difference, even if we said negative 10. Because remember, within 3 standard deviations of the mean, we have 99.7% of our data. So by the time you go out to 4, you're wrestling to split up 0.3% of the data. And then when we get out to 5, you know, it's still just 0.3% of the data. So, you know, I would say let's delete some of these zeros. I don't think it's going to change the answer at all, quite honestly. Yeah. I mean, it's just a little itty-bitty bit that's split between 3 standard deviations, plus, minus, and infinity. So, no, it's not going to make a difference. Okay? Alrighty. An airline knows from experience that the distribution of the number of suitcases that get lost each week on a certain route is approximately normal with a mean of 15.5 and a standard deviation of 3.6. What is the probability that during a given week the airline will lose less than 20 suitcases? Okay? So, what method are we going to use to solve this problem? Or what type of distribution does it have? It's normal. Okay, and if it's normal, then we're going to start with x, convert that to z, and then find our probability. So we're interested in the probability that x is what? Less than 20. Okay, I can convert that to a z-score. We get 20 minus 15.5 divided by 3.6. Okay. 3.6. All right, 1.25, very good. So this is the probability that z is less than 1.25. Okay, again, my upper bound is 1.25, lower bound is minus infinity. So second, number 2 is normal CDF, lower bound. I guess I won't put quite as many zeros since it doesn't make a difference. and upper bound is 1.25. Okay, and so we get 0.8943, which must be the answer that's not shown. Okay, questions about that? 0.8943. Okay, 8944 it says there. Alrighty. So the next problem turns the process around. It says the times for completing one circuit of a bicycle course are normally distributed. They tell us that, with a mean of 72.5 minutes and a standard deviation of 6.5 minutes. An association wants to sponsor a race, but only wants the top 25% of riders included in a trial run that should say what would be or should be the cutoff time. All right, so we know this thing is normally distributed, but what have they asked us to find in this case? Cutoff time. And in terms of x, z, and the probability, which one is cutoff time? Not z. Nope, sure isn't. It's x. X is our random variable. Okay, the random variable in this case is the time to complete the race. Okay, so they're asking us to find x, so we're going to start with the probability, and then we're going to convert backwards to the z, and then we're going to look at the x value. Okay, what probability did they give us that we're going to be able to use here? The 25%. Okay, so the top 25% of riders. Okay, again, remember x is your time to complete the race. Okay, so where are we going to put that top 25%? At the top? In the middle? Okay, try again. On the right? Okay. Nope, not on the right. Not in the middle. It's going to go on the left. Why is that? Something else. If we're talking about the top 25% of riders. No. No. Something about, think about the race. If you're in a race, the top scores, are they the longest scores? They're the shortest ones. The shortest times are going to be over here, right? The top 25% of riders, they're going to have the lowest times. Okay, that's why we put that 25% over there. Okay, so I can find my z value from this by using what on the calculator? We're going to use inverse norm, number 3. Okay, we tell it the area to the left, and so we get 3.25 is the area to the left. Okay, and so my z-score is negative 0.67. Okay, then from there we had a formula that allows us to find x. What's that formula? Negative 0.67. So to find x, we say x bar plus z times s. So we get 72.5 plus negative 0.67 times 6.5. Okay, type that up on your calculator. S is the standard deviation, sample standard deviation. Okay. Questions? Okay, very good. All right, what about question? Well, I think for me that, x, z in probability, or probability z and x, that's kind of the trigger. In this problem, we were given the 25%. We started with the probability. Okay, and they asked us to finish up with the cutoff time. That was our x value. So if I'm given the probability, I have to put that into inverse norm. Okay, what goes into that inverse norm function is a probability or an area, not a z-score. What it gives us out is a z-score. Okay, I don't know if that helps. Okay. 15. The body temperatures of adults are normally distributed with a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.6 degree Fahrenheit. If 36 adults are randomly selected, find the probability that their mean body temperature is greater than 98.4 degrees. Okay? What type of distribution does this have? Normal, because it says so. But what if it didn't say that? Suppose that wasn't there. What type of distribution would this have? Okay? Focus on what the problem is asking us to find. We want to find the probability that they're what? Mean body temperature. Okay, that's what we talked about with the central limit theorem, was that mean body temperature. Okay? And so when it comes to mean body temperature, we're looking at, we had a rule. If the sample size, the number of items we put together to come up with the mean, is greater than 30, then the distribution of those sample means is normal, approximately normal. Okay? So in this case, even if it didn't say normally distributed, we could say that this thing is normally distributed because of the sample size. All right. That's just advanced statistics, but that is the central limit theorem. When it's greater than 30, then we can assume that the distribution of sample means is normal. Okay. If the sample size is less than 30, but the original population was normal. For instance, if it had said normally distributed here, but let's say we only had 18 people in the sample, the distribution of sample means is still normal. Okay, so for a smaller sample size, as long as it started out in a normally distributed population, the means are still normally distributed. Key here is we want to find the probability that their mean body temperature. We're not looking at an individual person. Okay, we're taking 36 people, averaging their temperature, and then talking about what the probability is regarding that mean temperature. So we're interested in the probability that X bar is greater than 98.4. Okay? And we know that this thing is normally distributed because our sample size is large enough. All right? And so we're going to find the z-score. And it is 98.4 minus the mean is 98.6, but the standard deviation changes. It's going to be the original standard deviation divided by the square root of the sample size. So original standard deviation was 0.6. I'm going to divide that by the square root of 6, or rather square root of 36. Okay, that's all part of that central limit theorem. That is the central limit theorem. The central limit theorem, and go back and look at that video, the one about the central limit theorem. I'm sorry. Yeah. But make sure you check that out because you actually see it in a little demo, and I go through lots of examples about that. Okay, but anyway, So we're going to find the z-score. We get 98.4 minus 98.6 divided by 0.6 divided by square root of 36. So I'll just say 6 because I know that's what that is. I get negative 2. So probability that z is greater than negative 2. Okay, negative 2 is over here. We're going greater. So my lower bound is what? Negative 2. And my upper bound would be infinity. For normal, we always use CDF. We'll never touch PDF. So 0.9772. Okay. Questions?
Though this is a different theory, we still use the, when we're doing the normal CDF, we still use the smaller, bigger, random.
The syntax for that normal CDF on the calculator is always lower bound to upper bound. Okay? All right, number 16, a coffee machine dispenses coffee with a mean of 12 ounces and a standard deviation of 0.2 ounce. If a sample of 9 cups is selected, find the probability that the mean of the sample will be greater than 12.1 ounces. Still, the question we should ask here would be, what is the distribution? Okay? And our sample size is what? 9. Okay, so we can't say it's normal because the sample size is large enough. It doesn't say that it's normal, so technically either there's a typo here or we can't do this problem. Okay, this would be a good one where it should be added that the distribution of, what are we looking at? I guess the distribution of ounces dispensed. Is approximately normal. Okay, we need that because in this case our sample size isn't large enough for us to assume it otherwise. Okay, everybody understand? All right, so looking back at what they're asking us to find, we want to find the probability that the what? Mean. Okay, when we talk about probabilities of means, that lets us know we need to apply this central limit theorem if we've met the conditions. Okay, so we're interested in the probability that x bar is greater than 12.1. And so since we have added this statement about the distribution of ounces is approximately normal, then I can go ahead and convert this to a z-score. Okay, z equals 12.1 minus my mean of 12 divided by the original standard deviation, 0.2, over the square root of the sample size. So the square root of 9. Okay. So we've got 12.1 minus 12, okay, divided by 0.2 divided by 3. Okay, I got 1.5. Okay, that's my z value. So we're interested in the probability that z is greater than 1.5. Okay, and of course you can do that on the calculator. We're going to go from 1.5 to infinity. So we get 0.0668. No. You want to put something, start at least at 10. Okay, at 2, remember the empirical rule? Within 2 standard deviations of the mean, we only have, 95% of our data. So that would definitely throw you off. But I wouldn't do anything less than 10. Okay? All right, other questions? Okie dokie. Is this at all helpful? I feel like I'm just doing the problems. But okay, you have to think this way though, very systematically. Okay, let me. All right, 10% of the population is left-handed. A class of 100 students is selected. Convert the binomial probability of x being greater than 12, to a normal probability. Okay, so here, this one's kind of out of context. It's just asking you to do it. But we talked about using the normal distribution to approximate a binomial distribution. And we'll see a better example of this a little bit later. But in order for us to change from binomial to normal, we have to correct for continuity. And so we said that the number, in this case 12, in a binomial is 12. In a normal, we're going to represent this as a range, 11.5 to 12.5. Okay? Because when we talk about a continuous distribution like a normal distribution, whether or not you're greater than or equal to doesn't make a difference. However, in the binomial, greater than versus greater than or equal to makes a huge difference. So, if it says greater than 12, we need to be able to account for that differently than if it said greater than or equal to 12. Okay? So in the normal, we're going to say 11.5 to 2.5 is the interval that represents 12. However, I don't want 12 to be included, because here is strictly what? That's greater than. Strictly greater than 12. So that means I'm going to exclude this interval, but go beyond it. All right? So for a normal distribution, I would say probability that x is greater than 12.5. Okay? If in the binomial it had said probability that x is greater than or equal to 12, then in the normal, okay, since 12 is included, I'm going to try to cover the entire interval that represents 12 and go beyond it. So that'd be probability that x is greater than 11.5. Okay. And we went into a good bit of detail about that in the video on the normal approximation to the binomial. Okay, questions about that? Okay, let's look at this a little more in context. Here it says an airline reports that it has been experiencing a 15% rate of no-shows on advanced reservations. Among 150 advanced reservations, find the probability that there will be fewer than 20 no-shows. Okay. Still, we have to ask ourselves the question, what kind of distribution does this have? Very good. It's binomial. Did I say that earlier? Well, good. That's great.
I was just using it.
Excellent. Super. It's a binomial distribution. Okay. We've got two outcomes, either show or you don't show. We have a fixed number of trials. That's the 150. Probability of success is the same from trial to trial. And the individual trials are independent. So this meets all the requirements of the binomial. However, before we had these $100 calculators, it would have been quite a chore for us to have to calculate fewer than 20 no-shows. We'd have to calculate probability 0, plus 1, plus 2, plus 3, plus 4, plus 5, all the way up to 20, or use a table. Right, that it would take a while, right? And we didn't have the calculator to help us. So someone noticed that if we look at the probability histogram for a binomial distribution, it is approximately normal under certain conditions. And the conditions in the problems that we'll look at will be met. So we don't really have to worry so much about that. But here's how we're going to do this. I'll stop talking now. Okay, we're interested in the probability that there will be fewer than 20 no-shows. So probability that x is less than 20. Okay, I'm going to represent 20 as 19.5 to 20.5. Okay, and so when I write this as a normal probability, since 20 is not included, what am I going to say? Probability that x is less than what? 19.5. Very good. Okay, so this is over here for our normal problem. Now that we're calling this thing normal, anytime we have a normal distribution, we need to know two things. What? The mean and the standard deviation. So our mean for a binomial, which we said this is n times p. So n in this case is actually 150. P is 0.15. So it looks like we're going to get 22.5. Is that right? Okay, and our standard deviation is the square root of n times p times q. So the square root of 150 times 0.15 times what? So 0.85. If it's 1 minus 0.15, we get 0.85. Okay, I need my calculator to do that. Oh, yeah. Q is 1 minus P. Okay, so 150 times 0.15 times 0.85. Take the square root of that, which I'm going to be careful about. I don't want to let that go. Second answer. I got 4.373213921. Okay. All right. Now I'm going to put dot, dot, dot. I'm not going to write all those digits out, but when I get ready to calculate my z-score, which is next, I want to make sure that I include all of those things. Okay. All of the digits, because if we round, then that's going to affect our z-score, and then that's going to affect your final answer. Okay, so we got a mean, we got a standard deviation. Now I can calculate my z-score. Z in this case is equal to 19.5 minus 22.5 all over 4.37 dot, dot, dot. Okay, so let's do that. 19.5 minus 22.5 divided by, I'm just going to hit second answer. I get negative 0.69. So we're interested in the probability that z is less than negative 0.69. Okay, and of course we can use the calculator from there to get the answer. Normal CDF, that's correct. So number 2, and then we do minus infinity to negative 0.69. And so I've got 0.2451. Now, that's what we had to do before we had $100 calculators. But we do have $100 calculators now, and we could get close enough to the answer without doing it. In fact, we can get the exact answer. What the calculator will give us is exact. What we've done by converting this to a normal thing really is an approximation, but that's what the test is actually testing. I imagine that one day this concept won't be in statistics books anymore because we don't have to go through this process. You can do it on your calculator much faster. And if you decided to do that, that's perfectly fine with me. So I'm going to show you how we could get to the answer on the calculator. Ignore everything else that we've done, okay, because we're not converting anymore. So we don't have to do the continuity correction factor or anything. We're just going to treat this like a binomial problem. And so in the binomial, we were interested in the probability that x is less than 20. Okay, so in this case, again, 20 is not included. We'd already decided that this thing was binomial, but less than 20 includes from 0 up to what number? 19. So I can use, remember, binom CDF? It's the cumulative binomial function. And it's going to calculate for me probabilities from 0 up to whatever x I specify and add them up for me. Okay, so n in this case is still what was 150. P is 0.15, right? And then I'm going to put in 19. Okay, not 20, because in this case 20 is not what? It's not included. Okay, we want less than 20. So just do binom CDF. Okay, n is 150. P is 0.15, and x is going to be 19. And so we get 0.2509, which is the exact answer. Okay, but if you decide to do it this way, which saves you a whole bunch of time and work, you just have to be comfortable enough saying that 2.509 is closest to 2.451. Okay. Possibly. I mean, at this point, I personally would go on and do it the long way. Okay, because that in that case it was a little close.
But I mean, it's not even similar to the Indian.
That's true. So yeah. So as long as you're comfortable with that, that's fine. I mean, you know, it's an allowable cheat. Okay. I'm hoping, yeah. That's what I'm saying. I'm not guaranteeing. I don't know what the other answers are, but yeah. Okay. Just depends on how comfortable you are, you know. All right. I think, is this the last one? Oh, yes. Okay, good. All right. We're real close to the end. Telemarketer found that there was a 1% chance of a sale from his phone solicitations. Find the probability of getting 5 or more sales for 1,000 telephone calls. Okay, what method, where does this fall in the things that we talked about in this unit? Okay, greater than or equal to? What type of distribution do we have? Binomial. Very good. Okay. Huge chance. I mean, when it comes to figuring out the distribution, it's either going to say that it's normal, or it's going to talk about the probability of the mean, or, you know, it doesn't say anything. And then we have to kind of ask ourselves, could this be binomial? All right. So this is indeed binomial because they either get a sale or they don't. We got a fixed number of trials, 1,000. Probability of success is the same, and the trials are independent. Okay. So, but, you know, we could go through the long method like we just did, or we could use our $100 calculators. Okay? All right. We're going to try using our $100 calculators and seeing if we feel comfortable enough with our answer. What we're interested in is from 5 to 1,000. Okay? But, so what we don't want is what? And down, right? So to get the sum of 4, we say binom CDF. N is 1,000. P is 1%, so 0.01. And X is 4. What am I going to do with that? Make it what? Subtract it from 1. This is what I don't want. Okay? So we had 1 minus the part that we don't want. That's going to leave us with this piece. Okay? So let's do 1 minus binom CDF. Okay, 1,000. 0.01. And 4. And so I got 0.9713, which, you know, the closest thing to that is 0.9599. I got 0.9713. Just to be sure, huh? That's a little risky. 0.9713. The other answer was 0.9599. The only thing that came even close was 0.8810. That you want to see the long method? No, oh, the other answers. Okay. 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 Yeah. Okay. So what you want to do? Are we good or no? Okay. For those who want to be a little more precise. All right. We were interested in greater than or equal to 5. Okay. I represent 5 by saying 4.5 to 5.5. Okay. And in this case, it is included. So we're interested in the probability that X is greater than what? 4.5. Okay? That's our correction for continuity. All right, now I'm going to convert this to a z-score. So we say z equals 4.5 minus the mean. We said it was binomial, so the mean, very good. 1,000 times 0.01, so that's what? 10? Okay, that's our mean. And our standard deviation is the square root of n times p times q. Q in this case is, okay, so 0.99. All right, so our standard deviation comes up to I got 3.1464 for my standard deviation. You agree? Okay. Okay, good. So, all right, minus 10 divided by 3.1464, blah, blah, blah. Okay, so we find that z-score. 4.5 minus 10 divided by 3.1464. I get negative 1.75. Is that good enough? All right. So we're interested in the probability that z is greater than negative 1.75. Okay. So my lower bound this time is what? My lower bound, when I get ready to use... Nope, my lower bound. Negative 1.75 is here. You might need to draw it out. We want to go greater. So the lower bound is what? Negative 1.75. Okay, so we're going to do normal CDF from minus 1.75 to infinity. I get 0.9599, which is the answer that's on the test. So I did normal CDF. We will not touch normal PDF. Don't touch it. Okay. All right. The last question asks the standard normal distribution is distinguished by, and it looks like the first answer is the right answer, a mean. Oh, no, that's not the right answer. It's a mean of what? 0 and a standard deviation of 1. Okay. I know. Oh, there's one more problem. Let's act like we don't see it. Oh gosh. Okay. Oh, this is just another normal distribution problem. The amount of time between, yes.
On that last one, when you put the normal CDF into the calculator, did the higher upper thing need to be
Infinity.
as well?
Just infinity. Positive. I went from negative 1.75 to infinity.
It came up as an error.
Okay. Did you use the negative key and not the minus key? Yeah. That I don't know why they did that. That just was not necessary, but they did it. Okay. So with this one, I must have run out of things to talk about, and so I went back to the beginning. The amount of time between phone calls received by a switchboard has approximately a normal distribution with a mean of 4 minutes, standard deviation of 0.6, probability that the time between phone calls is between 3 and 5 minutes is. So they already told us it was normal. In this case, we're not looking at means, we're looking at individual calls. And so I would just look at probability that that 3 is less than x is less than 5. Okay, it's normally distributed, so I have to convert both of those values to z-scores. So we get z equals 3 minus 4 over 0.6. Okay, we'll say negative 1.67. All right, and then since 5 is 1 unit above the mean, then I don't even have to do a whole bunch of work. I know z is going to be positive 1.67. Okay, the mean is 4, right? In this case, and so 3 and 5 are going to be basically the same distance from the mean, except one's negative, one is positive. So we're talking about the probability that minus 1.67 is less than z is less than positive 1.67. And so I can use my calculator. And we're going to do second vars, normal CDF minus 1.67 to positive 1.67. I've got 0.9051. Those two are the same. Oh. Okay. 0.9051 or 50. We'll take that. Questions? All right, any questions about anything else?